Hello physics students, this is Dr. Brenzi here. This is lesson 4.1.6 and our objective for this lesson is that we'll be able to calculate or estimate the center of mass of systems and describe their importance. Before I start getting into center of mass and how to calculate it, we need to define some key vocabulary. So the first key term you're going to hear during my talk and during this lesson is what's called a rigid body. A rigid body is an object that doesn't bend or deform. So a block of wood would be a good example of a rigid body because it's not something that can get bent out of shape very easily or change its shape very easily. So that would be a good example of a rigid body. Now a non-example might be a towel, especially a towel that has been unfolded and is just crumpled up in the corner, because even when you try to throw it, a towel will start to unfold and it'll certainly change its shape. So a towel would be a non-example of a rigid body. The second term that you're going to hear in this lesson is what's called a point mass. Now a point mass isn't real, it doesn't exist in real life. But a point mass is a mass that we sometimes use in physics. It's kind of like an idea where all of the mass of an object exists at a single point. That is what we would call a point mass, or some physicists call it a particle. Those two words are used interchangeably. Now let's define what center of mass is. You might have a good idea of what center of mass might be already, but let's go ahead and define it just in case you've forgotten or you need a little refresher. So the center of mass of an object is a point that represents an average location of a total mass of a system. So if we have two masses, of equal mass, and they are a certain distance apart, then you can imagine that their average location would be halfway in between, and since they're equal mass, this would be the average location of the total mass of the system, is about halfway between those two. Now let's contrast that with this situation where we have a lot more mass at this end, and since there's a lot more mass on this end, our average location of all our mass is going to be a lot closer to this 500 kilogram block than it will be to this 50 kilogram block way over here. So our center of mass might be over here, and to tell you the truth, I would imagine that would be even closer to directly underneath this 500 kilogram block, but that's the way they drew it, and I just pulled the figure, so I didn't get to decide where that was. So think of center of mass as like an average location of all the mass that we have in our system. So how do we calculate center of mass? Well, there's a formula for center of mass, and I actually forgot part of it here. So what you do is you multiply the mass of each object times its position. And then when you're done with that, you have to divide that by the total mass that you have. And that's the part that I forgot. So let's try to do that with our seesaw here. And let's put a ruler on this thing. So let's say that this is 0, 1, 2, 3. Whoops. Okay, so I'm just making little tick marks here. 4, 5, 6. Ah, darn it. Well, it's going to be 6.5. Alright. And let's give these numbers. So let's say we're figuring out how far from the left-hand side is our center of mass. So let's call this 5, 6, and 7. And since we like to deal with MKS units, let's call these meters. Okay. So what I'm going to do is I am going to multiply the mass of this object times its position, which is 0. So x center of mass equals 500 times 0 plus Now, I have 50 kilograms times its position, and that position looks like it's at, I know it's really at 6.5, but I'm being lazy today, and I'm going to estimate that at 7, simply because I want the math to be a little bit easier for myself. But in reality, it would probably be 6.5, right? Okay, so we then have to divide all of that by the total mass, which is 500, plus 50. And we're going to get, in the numerator, we're going to get 350. Because that first term is 0. And then we're going to have to divide that by 550. Okay. And when we do that, we get a number that's approximately 7 over 11, which is equal to, if I remember right, 0.6060. We'll estimate that as 0.61. Okay. So the center of mass of this system, of these two objects, is actually right here at about 0.61. So I was right. So we would say that this location is the center of mass. Okay. Okay. So they actually drew that center of mass wrong. Oops. Okay. Now, if you're in advanced class, what I want you to do now is I want you to skip to the next slide. So you're going to have to fast forward in the video until you see this become yellow again. AP, stick around. We're going to actually figure out the center of mass in 2 dimensions. And I goofed up my formulas again. I have no idea why I didn't put M1 plus M2 plus ... underneath each of these. I'm so embarrassed. But I'm going to fix those now. ... And we have to do that over here. Okay. Okay, so when you're dealing with a center of mass in 2 dimensions, and you have a mass here, and a mass at another location, and a mass at a third location, what you can do is you can add up all the masses times their displacement vector. So you can either use a vector notation, or what you can choose to do is you can choose to split the vector into x direction and y direction, and then you can figure out the x and y coordinates of the center of mass. So let's assume that this is our origin, 0, 0. And let's figure out what the center of mass of this 3-body system is. Well, let's figure it out in x first. In x, we are going to have, for consistency's sake, let's call this number 1, let's call this number 2, and then let's call this one number 3. So m1 times x1 is 50 times -2 plus 50 times +1 plus 50 times +2. And we have to divide all of that by 150. Well, I could grab my calculator, but I quickly see that I have 50 times -2 here and 50 times +2. So those are going to add out or subtract out, however you like to think of it. So I'm just left with 50 times 1 divided by 150. So that I can quickly do, and that is going to be 50 over 150, or 0.3 repeating. So my x-coordinate of my center of mass is somewhere about 1/3 of the way between 0 and 1. About right there. Now I have to figure out what the y-coordinate is. So y center of mass. Okay, so for mass 1 we are at 0 y-coordinate. For mass 2, we are at -1 for a y-coordinate. And for mass 3, we are at +1 for a y-coordinate. And we need to divide all of that by 150. Okay. Now again, we could try to take out our calculator, but hey, let's use some thinking here. We have 50 times -1 plus 50 times +1. Those two add out, and we're left with 50 times 0, which is 0. So the y-coordinate of my center of mass is equal to 0. So what I would say is I would say that my center of mass, and I'm going to put it in blue, my center of mass would be located at 0.3, 0. So that's where the center of mass of this three-body system would be located. So that's how you can find center of mass in 2 dimensions. Okay, everybody, welcome back, advanced people. Alright, so how about estimating the center of mass, especially of rigid bodies? So for a rigid body, essentially what you want to ask is, where can I cut to get equal mass on both sides? And that place where you would cut will give you an idea of where your center of mass is. So we have, let's start off with this block of wood, and let's assume that it has equal density or uniform density. In other words, it's not, the particles aren't more packed in one place than they are in another. Well, if that's true, then I know that if I cut about halfway between the left and the right, I am going to have half of my mass on the left, half of my mass on the right. And since I'm dealing with something that's in 2 dimensions, I can make a cut in another direction where it's symmetric, like right here. And I know that my mass above is equal to my mass down, or below, excuse me. So this would be the location of my center of mass. Okay. So it's pretty straightforward for something that is a uniform shape, but what if we have something like a baseball bat where we have a little bit more mass on one end than on the other? Well, I have to kind of estimate, at least for now, let's say that I get about half of the mass on the left and half of the mass of the bat on the right. I'm just estimating here. Now there are ways to actually calculate this, but you would actually need to know integral calculus in order to do that. And even I think in AP you're not quite there yet. So for now we just have to do some estimating. So if I were to try to cut this in this other direction, I don't think I quite got that right, but you get the general idea. I would have equal mass above and equal mass below that line, so this would be approximately the location of my center of mass for my baseball. And you can see it's not halfway between the left and the right, because there's a lot more mass over here than there is down here at the handle of the bat. So that's how you estimate center of mass of rigid bodies. When we come together in class tomorrow, we're going to talk about, well, what if we had like 2 blocks and we had a block standing up on the, along with this block, how would you figure out the center of mass? And that'll be really interesting. But that's something I wanted to save for tomorrow in class. Now I want to end with, why is center of mass important? Why do we care about the center of mass of something? Well, the first reason, and this is a really huge reason, is that a rigid body obeys all the kinematic equations we studied so far, like Newton's laws of motion and the formulas we learned for displacement and velocity, and also the formulas for energy and momentum. Everything that we studied up until this point. Every rigid body obeys those laws as though it were a point mass located at its center of mass. So, When we've been talking about balls rolling up a hill or cars rolling up a hill, the whole reason that we can deal with balls and cars is because we can say that they behave as though they are a point mass located at their center of mass. So if you have a ball rolling up a hill, obviously the center of the sphere is where the center of mass is. And what happens is that this center of mass goes up, and as it's going up, it's starting to decelerate. It gets to a certain point, and then it's going to come back down exactly where it came. Now, if you were to contrast that with this point down here, this point does something really strange. It's going to end up doing some crazy motion like this, and then it's going to actually reverse its motion once it gets right there and do the very opposite. Now, that's certainly not something that we have studied in physics, have we? But we know that the center of mass has a nice motion that obeys all the laws of physics that we've talked about so far, unlike this point down here. So that's one reason why center of mass is important, is because it's the point on the rigid body that obeys the laws of physics that we've studied so far. Now, a corollary, or something that goes along with that, is that a rigid body can be held up against gravity if and only if you have a normal force or some other balancing force that is applied exactly under or over its center of mass. So what that means, and you've experienced this in real life, is that you have a young boy with a ruler here, and he can balance that entire ruler with just one finger, even though there's all sorts of mass over here and all sorts of mass over there. But because his finger is underneath the center of mass of the ruler, he can hold that ruler up against gravity with just a single finger. Now, it gets really interesting when you deal with other rigid bodies like two forks connected to a cork, connected to a matchstick, and what you can do is you can actually find that the center of mass of that object is exactly right where that matchstick is on top of that glass, and that's why this whole crazy thing balances on just that one little point. It's because that where that matchstick meets the glass is where its center of mass is, even though that center of mass is nowhere on this fork, or on that fork, or even on the cork. So a third reason why center of mass is important is because when we start getting into rotation, and sometimes we have things that rotate and move at the same time, a fancy word for move in physics is translate. So if we have something that is rotating and translating, we can split its motion into two parts and treat those separately. We can deal with the translation or the motion of its center of mass, and we can treat that separately from the rotation of that body around its center of mass. So we can treat rotation and translation separately. Down here in the corner, we see a gymnast, and he's doing a front flip. And as he's starting his front flip, what happens is that he is projecting his center of mass up into the air, but his center of mass follows a nice parabolic trajectory, just like we've studied with throwing balls. Even though other parts of him, like his feet, are doing some motion that looks like this, and then it goes up here, and then it will eventually come down and be lower than that parabola. So those are three reasons why center of mass is important, and you'll need to understand those. And you'll need to understand basically how to calculate center of mass, especially when you just have two, maybe even three masses. I'm going to kind of quiz you on that in the Do Now tomorrow, so be ready for that. Alright, so I think that's all I have for now. A little bit of a long video, but I'm sure there was a lot of information that you learned. And I look forward to seeing you in class tomorrow. Alright, bye.